Hi, today I'm going to do an example problem with simple harmonic motion. This is an A level, so this is about the position, velocity, and acceleration of something in simple harmonic motion. In this case, I'm going to have a mass on a spring. So the problem reads like this. A 1,200 gram doll is attached to a spring of spring constant 325 newtons per meter. The doll is pulled down 10 centimeters from equilibrium and released. So it's going to oscillate. Where is the doll when it is moving at negative 0.82 meters per second? And what is its acceleration when it's 2 centimeters from equilibrium? So in order to figure this out, we're going to do our standard problem solving. Let's just go with what do we know? We have a 1,200 gram doll. Okay, 1,200 grams. And I stop and I say, I need that in kilograms. So divide by 1,000. We got 1.2 kilograms. We've got a spring of spring constant, 325 newtons per meter. And we want to know where is the doll when it is moving at negative 0.82 meters per second. And what is its acceleration when it is 2 centimeters from equilibrium? Okay. There's our question. So if we draw a little picture, we've got a doll on a spring. So we've got our spring and then a doll. There we go. And it's going to be moving up and down in simple harmonic motion. And there's, I'm going to call that my equilibrium point. So it's going to be pulled down, it says it's pulled down 10 centimeters from equilibrium and released. So I'm going to have it pulled down 10 centimeters. And from, I guess it's from its middle, 10 centimeters, and then released. So bounce, bounce, bounce. Okay, we want to know where it is when it's moving at 0.82 meters per second, and what is its acceleration when it's 2 centimeters from equilibrium. So, the first question, where is it when it's moving at this speed? Well, what are we really looking for? What variable are we looking for? Where means position. So, I want to know what x is equal to when it's moving at negative 0.82. Well, that's what its velocity is, negative 0.82 meters per second. And that negative tells us, in this case, moving downward. So where is it when it's moving downward at negative 0.82 meters per second? Now, I have an equation for position. And the equation we have for position is a cosine 2 pi ft. The position is the amplitude times the cosine of 2 pi times the frequency times the time. All right, so what do I need to know? I need to know my amplitude, I need to know my frequency, and I need to know my time. Okay, so I need to know that in order to solve this problem. What can I figure out, or what do I actually know? Not a lot. So, well, actually, I do know something. I know the amplitude. Because if the doll is pulled down 10 centimeters, that's going to be its maximum position away from equilibrium. That 10 centimeters is the amplitude. So I do know that the amplitude is 10 centimeters. And I got to be careful, centimeters. So I'm going to put that in meters right away so I don't get myself messed up later. Frequency. Okay, frequency. I need to know the frequency of this thing. Well, I kind of look back at my notes and I say I have mass and I have spring constant. So I think I can figure that one out. So the frequency, we have that equation. 1 over 2 pi times the square root of k over m. So for this oscillator, square root of k, 325, over m, which is 1.2. So, all right, what do we get with that? If we calculate that out, we should get 2.62 hertz. All right, so we've got the amplitude, we've got the frequency. How on earth are we going to get the time? I don't have an equation for time. So what do I do? What do I do? Well, what information do I have that I haven't used yet? I've used mass, I've used K, I've used the 10 centimeters. I haven't used this piece right here. I haven't used the velocity. Is there some way we can figure out the time from the velocity? Well, what's our equation for velocity? Velocity is negative 2 pi frequency times amplitude times the sine of 2 pi ft. All right, so if I know my velocity, I know 2, I know pi. Hey, I just figured out f. I just figured out a, sine 2 pi f. Look at that. The only unknown is time. I can use this equation to get my time. Now, it's not going to be pretty, but I can do it. So I need to get time alone. So I need to get time alone on one side of the equation. Well, let's pop this stuff over here first. So I'm going to divide both sides by a negative 2 pi fa. That'll leave me with sine 2 pi ft on this side. Now, how do I get rid of a sine? In order to get rid of a sine, I have to do the inverse sine. It's just like if to get rid of a square root, you square both sides. So I'm going to do the inverse sine of both sides. 2 pi ft. And now I'm going to have the inverse sine of negative v over 2 pi fa equals the inverse sine. So I'm just doing the inverse sine of both sides. That cancels with that. So my next step, it looks like this. Negative v over 2 pi fa equals, well, just 2 pi ft. And at this point, to get t alone, divide both sides by 2 pi f. So t is going to be equal to the inverse sine of negative v over 2 pi fa all over 2 pi f. That's a big one. That's a really big one. So now I know all of these variables. I know v, I know f, I know a, I know f. I can solve this for time. So if we plug things in, inverse sine of negative 0.82 over 2 pi. My frequency is 2.62. My amplitude is 0.10. Oh boy. All over 2 pi times my frequency again, 2.62. And now be careful. This is the important thing with this. Anytime you see a 2 pi, that should trigger in your head units. If we're taking the sine or the inverse sine or cosine of something involving a 2 pi, we have to remember that we are dealing with radians. So anytime you see a 2 pi in a formula, you should realize we're dealing with radians. So right now, convert your calculator, switch it over from degrees to radians before you go any farther, otherwise you'll get the wrong answer. So in radians, when you do this, you should get an answer for the time of 0.0317 seconds. Is that a reasonable answer? It's pretty darn short. Pretty darn short. Well, my frequency was 2.62, which means that the period, if I just kind of mentally say the period is 1 over the frequency, I don't know, that's going to be about 1 over 2.5. It's going to be around 0.4. So a full oscillation is going to take around 0.4 seconds. So this is not that far past equilibrium, but okay. I guess it'll work. So are we done? No, we haven't even answered the question yet. The real question is, where is it? Now we go back and we can answer the position question because we have our time. And that actually isn't too bad. So x is going to be equal to the amplitude, 0.10, times the cosine of 2 pi times the frequency, 2.62, times the time, 0.0317. Ooh. And again, cosine of a 2 pi needs to be in radians. And if you do that, you get 0.087 meters. So, first answer, 0.087 meters. Does it make sense? Well, that's 8.7 centimeters. 8.7 centimeters is less than our maximum. So we're not that far off. Oh, I thought we'd be far off of equilibrium. We're actually not that far off of our maximum, our max point here. So if we got something that was more than 10 centimeters, we'd know we had an error because it's not going any more than 10 centimeters. So I think that seems pretty reasonable. So for our first question, we've answered it. It looks reasonable, and I think we're in good shape there. Now we can move on to answering the second question. What is the acceleration when the doll is 2 centimeters from equilibrium? Okay, so how do we do that? Well, I have an equation for acceleration. It looks a lot like what I was just erasing. And we can look at that acceleration equation and say, okay, what do I need to know? Oh boy, this is not erasing. So I'm not going to erase the information about my about my amplitude or my frequency, because I'm guessing I'm going to have to use that again. And that doesn't change based on, where the doll is. Those are consistent for the oscillating motion. So it's not, the frequency doesn't change just because I'm now interested in figuring out its acceleration instead of its position or its velocity. So don't erase that, keep that the same. Okay, so what's my equation for acceleration? We want to know what the acceleration is. So acceleration, negative 2 pi f squared times amplitude times the cosine, this is a big one, isn't it, of 2 pi ft. All right, what do I need to know? To get the acceleration, I need to know my frequency, which I have, my amplitude, which I have, my frequency, same thing. I need to know my time. I can't get the acceleration without knowing at what time this is happening. So I need to know at what time it's 2 centimeters from equilibrium. Okay, well, look at this. I have an equation for position. So can I use that? X equals a cosine of 2 pi f t. How much of this do I know? Well, I'm given the position. I know my amplitude. I know my frequency. I can get time from here. So it's kind of the same thing as what we did to figure out where it is. Just we're using a different formula to figure out the time. Once we have the time, we're going to pop it into the acceleration formula. So here, all right, I need to get time alone. X over a, let's divide both sides by a. X over a equals 2 pi ft, cosine 2 pi ft. To get rid of the cosine, I'm going to do the inverse cosine of both sides. Inverse cosine of x over a equals 2 pi ft. Get rid of the 2 pi f by dividing both sides by 2 pi f. So it's going to be the inverse cosine of x over a over 2 pi f. I know it all. I can solve for my time. So this is going to be the time at which the doll is 2 centimeters from equilibrium. So inverse cosine of x, which is 2 centimeters, careful, we need to convert to meters, over amplitude, all over 2 pi times my frequency. So when I do that, I get a time of what? 0.083 seconds. And again, it's pretty short, but I mean, the last time we got 0.032 seconds, so this is pretty short. I'm going to say it's reasonable, though. Let's see what we get for our acceleration, then. So our acceleration is going to be negative 2 pi f, 2.62, and, oops, I'm going to put those there, times 0.10 times the cosine of 2 pi f, I'm running out of room, t, 0.083. Wow. Okay. And now let's see if I can erase this without smudging it all over. Ha. Again, 2 pi and a cosine means we have to be in radians. So we have it all. We can calculate it and figure out what our acceleration is. In this case, don't lose that negative sign out front. Our acceleration is a negative 5.4 meters per second squared. So acceleration is negative. So that means we're accelerating downward. You might ask yourself conceptually, if we're accelerating downward, where are we? Are we going to be above equilibrium or below equilibrium? Well, when we're above equilibrium, we're speeding up until we hit equilibrium, and then we slow down. So if we have a downward acceleration, we need to be speeding up going down, which would be, yep, up here, moving downward. Or we could be moving upward and slowing down. So the other place we could be is upward and slowing down below equilibrium. So those are two possible places where we could have a negative 5.4 meters per second squared. And we know that both of those are going to occur 2 centimeters from our equilibrium point. All right, so we've answered the question. It's pretty fast, but it's less than gravity, so I think it's going to be pretty reasonable. If it was more than gravity, this doll is going fling way off and not going to stay on its spring. If it was 0.000006, I'd say we have something wrong. So that's what we've got for that question. Now I want to do one more part with this type of question. I want to go over what the maximum values are. So we have these answers, but it really is hard to know if this is the right answer or not, because what does an acceleration of 5.4 mean in simple harmonic motion? So one of the ways you can kind of check to see if numbers are making sense is to figure out if your numbers are all smaller than the maximum that these numbers can be. So, come on. I want to figure out what the maximum values of position, velocity, and acceleration are. So, how are we going to do that? So I'm going to go back to the basic equations for position, velocity, acceleration, and let's take a look at them. So position is amplitude, times the cosine of 2 pi f times time. Velocity is negative 2 pi f times amplitude times the sine of 2 pi ft, and acceleration negative 2 pi f squared amplitude back to cosine. And if you remember from first semester in your calculus, the velocity is the derivative with respect to time and position, and acceleration is the derivative of the velocity. So the derivative of the cosine gives us a sine. The derivative of the sine gives us a cosine back. So flip, flip, flip. All right, so I want to figure out what the maximum values are. So what would x max be? Well, okay, if you think about it, you already know what the answer is. What's the maximum position? That's how we define our amplitude. We know it has to be the amplitude. But how can I tell that from the equation? So the equation has amplitude times the cosine of something. I'm just going to ignore the 2 pi ft for now and say the cosine. A cosine function is back and forth, and it varies from +1 to -1. So this part of the equation right here, the biggest it can ever be is 1, because the biggest the cosine can ever be is 1. So this whole thing right here, I'm going to say the maximum is when that is 1. Well, okay, does that work? Yeah, it's the amplitude times 1. Yay, okay. Okay, yeah, we just proved that the amplitude maximum position is the amplitude. Very exciting, I know. Let's do something a little more exciting. How about the maximum velocity? How fast does this thing go? And if, again, think conceptually, when is it moving its fastest? So it starts at rest at its peak, and then it speeds up until it hits the equilibrium, and then it starts slowing down to rest. Speeds up, slows down. Its maximum speed is at that equilibrium point. What is the number for that maximum speed? If we look at it again, now we're dealing with the sine. So we have sine, and the sine, what does that vary from? Well, +1 to -1. So the maximum for the velocity is going to be when that sine term becomes 1. So maximum velocity is just simply 2 pi f times the amplitude. And now there's a negative sign there, but does that matter? No, it's just saying if maximum velocity is either up or down. So the number, if we just want the number, 2 pi frequency times amplitude. And same thing with the maximum acceleration. The cosine has to go between 1 and -1, so the biggest the acceleration can ever be is when this whole thing is 1. So 2 pi f squared times our amplitude. And again, I don't care about that negative sign. I'm just looking for the number. So if we do this for our situation, we can actually calculate that the maximum is, okay, 0.1 meters. Vmax, the maximum velocity of the doll, is 2 pi FA, and I get 1.65 meters per second there. And the maximum acceleration, I get, what do I get? Ooh, 27, big, 27.1 meters per second squared. So are our numbers that we got for the first two questions, are they reasonable given the maximums we have here? Well, yeah. We had a position of 8.7 centimeters. We're fine there. We had a velocity, we were given a velocity of 0.82. Okay, yeah, that's less than that. And we had calculated an acceleration of 5.4, which is less than our maximum acceleration can be. So that's a good way to test that you have reasonable answers. If you get an acceleration that's bigger than the maximum acceleration, you know you have an error. So that can be something useful, and some of the assessment questions I might ask you to calculate some of these maximum values. And it really isn't hard. All you have to remember is that the biggest that a cosine or a sine can be is 1. So the biggest that any of these can be is when the sine or cosine part of it is just 1. All right, I think that's all we've got for simple harmonic motion. We've answered the questions, we've thought about it conceptually. I think we've done a good job. All right.